All right. Well, here we are, parallel axis theorem. Okay, this is the second to last section. And this is a very brief kind of running you through how it works. Okay, so you can pivot, believe it or not, you can actually rotate objects about any point you want, right? There's nobody that's going to stop you from doing that. So, for example, we typically rotate disks about their center of mass, but there's actually nothing stopping you from rotating it about this point right here. Nothing's going to stop you from doing that, okay? But when you do that, it actually changes up the moment of inertia of that object, okay? Because now more mass is located further from the center of mass. Okay? Now, if you consider this object, right, let's pretend that we have a disk and we initially are spinning it about the center of mass, but then we decide that we want to move the axis to the left over here, then we can actually relate the original moment of inertia to the new one. And that's what the parallel axis theorem does for us. Okay? I sub d is our new moment of inertia at the point d from the point that's a distance d from the center of mass. That's going to give that in order to get that moment of inertia, I would need to do the moment of inertia about the center of mass and then add md squared to that equation. Okay? This right here is the rotational inertia, okay, about the CM, about center of mass, and this right here is the rotational inertia, okay, of the object's equivalent particle, okay? So what that means is that we basically approximate the rest of the object as a particle, a point mass, pivoted about some axis, right? Okay, and then just to prove to you that this is legit and not me making stuff up, um, if we take, for example, this is the parallel axis theorem, okay? And let's say that we want to start with a rod pivoted about the center, but we want to move the pivot to the end of the rod. So, for example, we have like a rod right here, okay, and it's pivoted about the center, but we want to move it to a rod that's pivoted about the end, okay. Either way, doesn't really matter. And let's say it's a length, we can say it's a length L, okay. Then when I shift it, okay, sorry, that should be an equal sign right there. When I shift the center of mass or the pivot point, my new moment of inertia is equal to the original, which was 1/12, okay, mr squared, or I guess I should say ml squared, okay, ml squared, okay, plus m, and then my distance is going to be half the length of L, because if this whole thing is L, okay, then this is 1/2 L, okay? So this is going to be 1/2 L squared, okay? Well, when I do that, I end up getting 1/12 ml squared plus um, m 1/4 L squared, okay? And then you see that I have a common factor here, 1/12 ml squared. This is 1/4 ml squared. And I can actually get a common denominator. Okay, I can do common denominator to get that. If I turn this into 3/12, okay, multiply top and bottom by 3 on the right side, and I end up getting, this ends up being 1/12 ml squared plus 1/4 ml squared equals I should have wrote that in over 12. That's 3 over 12. It becomes 4 over 12 ml squared. Hey, wait a minute. 12 m over squared. M times L squared. That's just going to be, okay, 1/3 ml squared. Okay. That simplifies out. Okay. So there's that. Okay. A uniform disk of mass m and radius r is pivoted about a point P that is on the edge of the disk. So now instead of pivoting about the center, we're pivoting it about the end. Okay. And so one thing to notice really quickly is that here's where the original center of mass was. Okay, there's the distance to P. Okay, and what happens is when we rotate it, okay, it's going to go, okay, right there. Okay, and that's going to be important for us to know here in a minute. So when I do the new moment of inertia for this, I'm doing ICM plus plus m, the distance d. Okay. Well, in this case, the distance d is just the radius r. Okay. So this is going to become 1/2 mr squared plus mr squared, which is just 3/2. Okay. mr squared. Okay, that's all you got to do for that. It's also important to note that you've got speed and it says lowest point. Okay, so you're asked to find a velocity at a point, so you'd have to use energy transformation for this problem. So when I use energy transformation, what I'm going to do, okay, is I'm going to do mg delta y, because it starts out at some height, and it's all going to turn into rotational, 1/2 I sub d omega squared. Okay. So now, or I guess I should say I sub p, because it's at about point P, okay? Okay, so now when I plug everything in, okay, I'm going to get mg, my delta y, my height, well notice the height here is, wait, it's the diameter, it's 2r, okay? My diameter is 2r right there. So mg 2r, okay, equals 1/2 times 3/2, okay, mr squared times omega squared, okay? I'm just plugging everything in. And you'll notice that you can actually make a couple cancellations here, okay? You've got m on both sides here. You can cancel out one of your r's, okay? And you'll be left with 2g equals, this is going to be 3/4, okay? 3/4 r omega squared, okay? Multiply both sides by 4 to get 8g equals 3r omega squared, and then we need to end up getting what omega is, okay? So omega squared is equal to 8g over 3r, and then take the root of that to get your solution, 8g over 3r, okay? Now that's not the answer because it asks for speed, which means I need to figure out what v is. Not omega, I need to figure out what v is, okay? Okay. So what I'm going to do is v equals omega times r, so that's just going to be root 8g over 3r, okay, times r, okay? And that's going to be the velocity right there, okay? Okay, so there's that. And then the final part right here is now that you have a hoop, okay, so now instead of us pivoting a disk, it's now a hoop, okay? When the center reaches its lowest point, will it move faster, slower, or the same speed? Well, the hoop has more inertia than the disk. It has a greater moment of inertia. So it should actually move slower than disk because hoop has more inertia than disk. So it is harder to get moving. Okay? And also harder to speed up the rotation. Okay, that's another important point to make there. Okay? All right, well that's the parallel axis theorem. Okay? All right.